let's see here. I think I've got everything. Yep. Okay, so yeah, well, while we're waiting for Audrey to join us, let me show you what I worked out. So we, last time, you know, he says in the middle of the proof at the end of section 1.3, he says it's a simple exercise to show that the unit ball with respect to this norm is compact.
Oh, yes.
So did you work it out, or?
No, I've been working on some physics.
Yeah, that's cool.
I plan to hopefully we can get caught up in the exercise.
Well, you know, I mean, it's okay to have some, you know, things missing here and there, and here it's you know, I think it's better to see the forest than the trees in this particular topic sometimes, you know, like it's okay. But
this weekend I plan to.
it's really okay. So I just wanted to show you my argument for it. So if we look at the, let's say B equal to the closed unit ball of radius 1, right? So that was x in E such that the norm of x is what, less than or equal to 1, right? I mean, that's the space, and the claim is that the context here, and this is from page, you know, basically 18 and 19 of the book. He says it's a simple exercise to show that the unit ball with respect to this norm is compact. All right, so this is the unit ball. The norm, remember, is here. He's got basis, right? E1, E2, ... En. All right, and so that means that, you know, if we so we can, let's consider sequence in you know, sequence in the unit ball, right? And what we have to prove that the unit ball is compact is we have to prove that there exists a convergent subsequence, right? Yeah. So let me introduce some notation, which is that x sub j is equal to alpha 1j E1 plus alpha 2j E2 plus alpha n j En, right? And remember, we can, without loss of generality, use the norm, which is given by just adding the, you know, yeah, exactly. Yeah, modulus or absolute value of these coefficients, yeah. All right. Okay, so what I say is, all right. So what I say is, let this define, let's say, big B sub j, all right? So this defines a real sequence, right?
Yes.
And, okay, by construction, this is less than 1, right?
Yeah.
Because it's the norm of the sequence in the unit ball. So yeah, it's less than 1. Or equal to 1. Less than or equal to 1. Less than or equal to 1. So it's a bounded real sequence, right? So therefore, by Bolzano-Weierstrass, right, there exists, you know, beta, let's say j sub p, which converges to b, right?
Just some value in b.
Some, well, that's some real number.
Yeah, okay.
I mean, it's convergent, is my point.
Yeah.
Now, more than that, though. Likewise, if we look at it, the norm of alpha, let's say k jp, right? You know, this is also going to converge to some, let's say, beta k. How do I know that?
So the norm, is that the norm of terms?
Though I'm just talking about the absolute value of the kth one of these guys, right?
Yes. Okay.
It is smaller than the beta j,
But it's also monotonically increasing.
right? But yeah, I mean, the thing is, we know that the beta jp is converging to b, and essentially, so if we look at this, I mean, you could write it down, the norm of alpha k jp, right, is less than so my point is that if this sum converges to B, right, for this subsequence,
Yeah.
it must also be for that same subsequence, this converges.
Okay. Because it's dominated by.
Yeah,
Okay.
I think that's reasonable. Yeah.
Oh, yeah. Did you see what I commented in the YouTube?
Maybe.
You,
Just hold.
like, I don't know if you ended up doing it afterwards.
Oh, you're talking about the D and the epsilon.
Oh, yes.
Yeah, I saw what you're like. I eventually circled back and said what was right, right?
Yeah.
Yeah. Okay. So.
The other one, first half of that theorem that uses Reason's lemma, and I was just like, it has to be bounded, like just by the definition of bounded.
Yeah.
It's a ball. And then all you needed was the closed bit, and it was closed because if you just, like any mapping, if the free image is closed, if it's a continuous map, and the free image is closed, that means the image is closed. I think, right? Yeah, if it's continuous, because it maps closed things to closed things. And so, like, that's all you need for the first part, because you just have to show that compact means bound. Like, if you have finite dimensional, you have bounded.
Yeah. No. At the moment, I'm just focusing on proving that the unit ball in finite dimensions is compact.
Oh, yeah. You can just construct the subsequence.
Well, that's what I'm doing right now. So.
Oh, okay. Sorry.
No, it's okay. It's okay. Because I started trying to do this in the last lecture, and I just couldn't quite see my way to it. And it is using the basis, right? Like the fact and the norm. So you take the sequence, expand it in the basis, and then I notice I've got a real sequence which is bounded. I pick a convergent subsequence, and notice that implies that for that same subsequence, these guys have to also separately limit to something. Because if any of them diverged, that would contradict the convergence of the BJ. And anyway, so then, now that I have all that, we can let x equal to beta 1 E1. See, the thing I was struggling last time is I couldn't think of how to construct the limit sequence to which it was going, But now I see it. See, so... and then you can argue that the norm of x jp minus x is, well, that's literally equal to the absolute value of alpha 1 jp minus beta 1 plus plus alpha n jp minus beta n. And those all go to 0, right, by the construction of the betas. Like my point, I said beta is the limit of each component sequence. And so this goes to 0 as p goes to infinity, which is to say that this is a convergent subsequence in this particular norm. And as we proved, all norms in a finite dimensional context, all norms are equivalent, so convergence in this one norm suffices. And the only thing that's left in terms of this proof is what is the only thing left I have to show?
Well, it needs to be in the unit ball.
Right, I need to show x is in the unit ball. Can you guys tell me why x is in the unit ball? Because if I have that, then I'm done.
Well, it's converging to x, but x is in the span.
Right. Yeah. What specifically is the norm of x? It's the norm of this, right?
Yeah.
Which is.
Yeah, the norm of x is 1 though.
It's this one, right? But yeah, I'm just going through the construction. So I mean, I agree with you, Audric. So it's this, but that's equal to beta 1. These are positive, yeah. But that is exactly what I called b. I mean, that is going to be b, which is less or equal to 1. See, because if you add together all the betas, that's just adding together the absolute values of all the component subsequences, whose sum is by definition the b sub j, which we have pointed out by the initial application of. I only apply a Bolzano-Weierstrass once to the sum sequence, and then I'm using this kind of. So like the thing that was blowing my mind a little bit was trying to think about how to apply Bolzano-Weierstrass to like each component, and then somehow string together all those subsequences to find some sort of universal, glorious, common subsequence, and that was like hurting my brain. And so I decided, oh, wait a minute, I need to work on something that picks up on the totality of all the components and then go from there in order to find the convergent subsequence, and there it is. There are probably other ways to attack this. I mean, so when you're working with limits or limits of sequences in a finite dimensional vector space, you can prove that the multivariate limit exists only if all the components exist and match. Like there's a vector limit theorem that if I had already proved, it probably would make quick work of all this. But I haven't done that in here, so I was trying to, right?
Thank you very much.
So yeah, Audric, that's all you missed. I was just doing that because, it's not really what we're talking about today.
Okay.
I was trying to burn a couple minutes here while you were setting stuff up. So.
Yeah. Oh yeah, I got accepted in the UTA.
Woo!
Congratulations.
Yeah, I got an interview. I have an interview for the TA position next week.
Cool. And so, well, you don't have to say on camera here, but yeah. We'll talk more about it later.
Yeah.
Because my mic does sometimes pick you up. Okay, so let's go on here. So we defined Banach space last time, right? And a Banach space is a what? A complete normed linear space, right? Complete meaning that every Cauchy sequence converges. And, example 1.46. So let's see here, talk about Banach spaces some more. So this is a complete normed linear space. Complete meaning each Cauchy sequence converges. And it converges to a point within the space in question, right? So, all right, so example 1.4.6, it simply says that the L2 space is complete. All right. All right. And then I'm going to forego the details in that one, okay? I'm going to move on here to example 1.4.7. And another important example of Banach space is the space of continuous functions. So C, A, B. Let's say continuous. And we're just going to say, for the sake of specificity, real valued, but he points out that these arguments really just hold as well for complex valued functions on the closed interval, right? And what's the norm? Here, the norm of f is going to be the max norm, right? Max on AB, absolute value of f of x. All right. So I think this example is a little bit more important than the one I just skipped because it should help us understand better what uniform continuity means and how that works. And all right, so let's get into it here. So he says, so our goal right now is to prove that this is a Banach space, okay? So to do that, we need to take a Cauchy sequence, right? So let's, consider Fn Cauchy sequence in this space, all right? And he says pick epsilon greater than 0. There exists n sub 0. You could say a natural number. Yeah, n sub 0 in the natural numbers, such that what? The norm of Fn minus Fm is less than epsilon for m and n greater than or equal to n naught, right? So this is just the definition of Cauchy sequence, all right? Now, what does that mean? Look at the max norm right above it. So we can immediately get from that something about the values. See, so this is defined to be that, right? So this implies that the absolute value of Fn of x minus Fm of x, right, must be less than epsilon for all x in A to B, right? Does that make sense? I think that makes sense. No, I'm just literally saying that this condition is the max norm, which is here. So we're taking the max of Fn minus Fm, right? Which is Fn of x minus Fm of x. So whatever that value is on A to B, it can't be bigger than epsilon. Otherwise, this would be larger than epsilon. So just that. Now you're saying that what you're saying might be true, but you're saying that this means something else, right? This means that for any x in here, right? So thus, for any x in AB, we have the sequence Fn of x is Cauchy sequence in the reals. Because that's that's the absolute value. So, and of course that could be modulus if you want to comment. So that's a Cauchy sequence of the reals. And consequently, since we know the reals are complete, right, we can thus set f of x equal to the limit as n goes to infinity of fn of x, right? We know that that exists, all right, because, and we can do this for each x. You see? So for each x, we can construct f of x by the limit of this Cauchy sequence. And this is, again, for all x in AB. So all that does is defines a function, right? We don't know the properties of that function yet, right? But he points out that we do have what? So he says, observe that the absolute value of fn of x minus f of x is less than or equal to epsilon for all n greater than or equal to n naught and x in AB. So he's going back up to this guy right here, I believe. He says basically take the limit as m goes to infinity on this, and it gives you that. All right. Okay. So what remains? See, what we'd like to do is we'd like to show that, you know, yeah, we want to show that the initial Cauchy sequence, in fact, has limit this function defined in that way. But for it to be in the space, we need to prove it is continuous. Okay. So therefore, towards that end, let x naught be an element of A to B. All right? And then he says, since f and naught is continuous, right, on A to B, there exists delta greater than 0 such that the absolute value of fn sub naught of x naught minus, he's going to introduce another variable here, y, all right, is less than epsilon for y in the closed interval to A to B, such that what? Such that the distance from x naught to y is at most delta, yeah? X naught minus y less than delta. So that's the usual epsilon delta continuity condition, right? Then, check this out. So we take the absolute value of f of x naught minus f of y, right? And that, by the triangle inequality and adding 0, is less than or equal to the absolute value of f of x naught minus fn sub naught of x naught, closed absolute value, plus new absolute value, fn sub naught of x naught minus fn sub naught of y, closed absolute value, open a new absolute value, fn sub naught of y minus f of y. And tracing back everything that we've just set up, that's less than epsilon plus epsilon plus epsilon. Let's see here.
such that we have what we want.
Right. And you see, of course, that we can go through the same argument again, right? Let epsilon be greater than 0. And we can retrace our steps, right? And we can replace epsilon with epsilon over 3, and the next epsilon with epsilon over 3, and the last one with epsilon over 3. And then when we get to this final step, we go epsilon over 3 plus epsilon over 3 plus epsilon over 3. Epsilon, woohoo, continuous, right? Therefore, we took an arbitrary Cauchy sequence, and we showed that with respect to this max norm, there exists that it converges to a function, right? And that function is also continuous. So it's in the space, which then proves, of course, that this is a Banach space. Does that make sense, Audric?
Yeah, once I wrestle with that, yeah.
Yeah, I know. It's easy to lose track of what's the n naught, what's the x naught. You know, I mean, but.
Like these are all things we've done before, so
But yeah, it ultimately rests on the fact that the norm directly gave us a Cauchy sequence of the values of the function's difference. You know, that gave us a Cauchy sequence in R, and so I don't think you would have any trouble modifying this proof if we were looking at functions on the closed interval, which were, let's say, finite dimensional vector space valued. I think the same proof would go through, because as long as your vector space is complete, I mean, you probably could even go so far as to say continuous Banach space valued functions on the closed interval. As long as the range, as long as you get like a Cauchy sequence of the, as long as you define the norm on that thing the same way. I guess the question is, would max make sense on the Banach space? So there's the rub. There's the rub. But max would make sense on a finite dimensional vector space. So at least you could replace RC with a finite dimensional vector space. You can still talk about max on that. You could talk about them.
saying this is a test question?
Probably not. This is a test question. That's funny. Okay, so let's move on. Okay, so next up, let's see here. Oh, I think I forgot to say the conclude. I mean, one of the things we could say is that the sequence, yes, the sequence Fn converges in the max norm, right? But in the other way of saying things, the sequence Fn converges uniformly. It's uniformly convergent to F. All right, so like uniform convergence is convergence in this norm.
Because it doesn't depend on a single point.
Yeah, right. So, and of course, a typical real analysis class would talk about uniform convergence without talking about all this, some of the bells and whistles here. So, all right. So next we're talking about conditional convergence and series and such. So definition, series, sum n equals 1 to infinity of x sub n in normed linear space. E is convergent if what? The norm of x1 plus x2 plus da 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 plus xn, right, minus x goes to 0 as n goes to infinity for some x and e, right? Which is just symbolically saying if the sequence of partial sums converges, right? So a series is convergent if the sequence of partial sums converges. And we write, what do we write in that case? As usual, right? The sum n equals 1 to infinity of x sub n is equal to x in that case, right? So also, if you have the sum n equals 1 to infinity of the norm of xn is less than infinity, then the series is called what? Right, yep.
Would that be the same here?
Yep, same here, absolutely convergent. So same terminology. All right, as he points out, in general, an absolutely convergent series need not converge, as can be seen from example 1.43. Where is that? The polynomials? Let's see here.
Well, that looks like the exponential series.
Oh, yeah, I got it. So like, yeah, inside. We had in this polynomials in 0 to 1, we considered Pn of x, right, equal to 1 plus x plus da 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 plus 1 over n factorial x to the n, right? Why is that absolutely well, that's absolutely convergent.
Because the numbers themselves are always positive, so it's wrong there.
Yeah, if we take the norm of this thing, right, which is the max of that on 0 to 1, it's, yeah, exactly, it's 1 plus 1 plus da 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 plus 1 over n factorial, plus 1 over n factorial, right? I think that is the max of that. And of course, that is less than e to the 1. Because the exponential is just adding the tail of that partial sum on. E to the 1 is, e is just what you get if you keep going forever and ever. So of course, yeah, that's absolutely convergent because
They converge to a point.
yeah.
Not zero. I have a question on the notation. So when you say the sum of the norms, that's literally like norm plus norm 1 plus norm 2, and
Yeah.
like the norm of all the points, like we did up top.
Right.
Okay.
Yeah, this is, okay, so this is a real series,
Yeah.
whereas this is a sum in the vector space, right? Yeah.
Yeah. Okay.
All right.
I just wanted to make sure.
Man, this time of day, all of a sudden it hits me. I get like super tired this time in class. I'll tell you what. What's wrong with me? All right, so theorem. A norm space is complete if and only if every absolutely convergent series converges. Theorem. Normed linear space E is complete if and only if, what did I just say? Every absolutely convergent series converges. All right. Let's give it a go. Should I start the proof here or start the proof over there? What do you think? Can I erase?
Yeah, you start.
I think we'll remember the definition of series, right? We don't need to take up half of my precious board space on that. Let's see here. All right, so let's attack this proof, see if we can make sense of it. He says, let E be a Banach space. Banach space, and suppose xn is an element of E, and we've got it's absolutely convergent. All right. Let Sn be the nth partial sum of this guy, x1 plus, not that one, but this guy here, x1 plus dot 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 plus xn. All right, for n equals 2, 1, 2, and so forth. Excuse me. Yowzers. We need to show that this is a Cauchy sequence. So I think right now we're working on the converse, right? We're assuming that
Arbitrary series, absolutely.
is that right? What are we working on here? Oh no, we are assuming it's a Banach space. It's the forward direction, right? So if E is a Banach space, that's a normal linear space which is complete. So, oh, I think I might have lost Audric.
No, I'm still here. They asked me to move.
Oh, how dare they? Let's see here. Like, come on, it's my only class. Let me be. Let's see here. So, where was I? So, Banach space means it's a norm linear space which is complete. We're now trying to prove every absolutely convergent sequence converges. So, okay, so we've assumed our absolute convergence. Now we're trying to show that it converges. Okay, this makes sense. So now we've got, to show it converges, we need to show that the limit of this sequence exists, right? And a good way to do that apparently has something to do with the completeness, right? So if it suffices, then it suffices to show that this is Cauchy, because if we show that's Cauchy, then that proves that it's convergent because we're in a complete space. So our goal at the moment is to show this is a Cauchy sequence. If we can do that, we got it. So let epsilon be greater than 0 and k a positive integer such that this tail of the, basically here, I call this the tail of the series of norms, yeah? So this has to be less than epsilon, right? We can do that because we're given that the series converges, right? So then what? He's like, okay, so then for every m and n, and without loss of generality, m greater than n greater than k, right? We have the norm of Sm minus Sn, which is going to be what? So there's a cancellation, right? The first n-fold terms cancel, and we're just left with xn plus 1 plus da 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 plus xm, right? But by the triangle inequality, that is less than or equal to the norm of xn plus 1 plus da 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 plus the norm of xm, right? Which then, of course, is less than the whole kit and caboodle here, yeah? Right. And, well, man, you know, eh. Does he use a different letter? R, thank you, that's better. R. Yeah, we shouldn't use n here. N has a different meaning. So this is x sub r less than epsilon. Listen, so like up here, you could just as well have said r and r, and maybe it did in the book and I just missed it. That's just a label. The k is what's fixed. All right. But anyway, therefore, what have we done? Hence, SM Cauchy, which implies that SM, or let me say SN, is convergent, yeah. And what does that mean?
Oh, it is the series itself.
So yeah, therefore the series converges. So we're done, right? Well, we're done with that half. Now we do what? Yeah, the converse direction, so likewise, E is a norm space, norm linear space, in which every absolutely convergent series converges. And as he says, we need to prove E is complete, all right? So, okay, to prove E is complete, what do we want to do? Well, we take a Cauchy sequence, right? So let xn be Cauchy sequence. Right? And then what is that entitled to? That entitles us to many things, right? But in particular then, for every k, in the natural numbers, there exists pk in n such that what? The norm of xm minus xn is less than 2 to the minus k. When is that happening? That is for all m and n bigger than or equal to that pk. Yeah. All right, he says, without loss of generality, we can assume that the sequence Pn is strictly increasing. All right. Thus, what? Since the series sum k equals 1 is, all right, well, let me write this down. That's that's too much for me to say. So then he's like, he says the series k equals 1 to infinity of xp sub k plus 1 minus xp sub k is absolutely convergent. Do you believe that? Why is it absolutely convergent? What's going on here? So Audric, are they just, what happened? You're so quiet all of a sudden.
Yeah, I'm usually more talkative, but
Okay.
I'm just going to rewrite everything right now.
Oh, okay. So to say that's absolutely convergent means we need to take the norm of it, right? So if we look at the sum, k equals 1 to infinity of the norm of xp k plus 1 minus xpk. Well, I believe that that is less than what? Well, I mean, that's less than or equal to the sum of what? K equals 1 to infinity of 2 to the negative k, right? So 1/2 to the k, also known as the geometric series, 1/2 over 1 minus 1/2, also known as 1. So yeah, it's absolutely convergent. This is a pretty typical move, using the geometric series with a radius of 1/2 for this kind of argument. Anyway, so yeah, it's absolutely convergent. And therefore, by our assumption, it's what? It's convergent. Thus, the sequence xpk equal to xp1 plus parentheses xp2 minus xp1 plus dot 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 plus blah, 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 xpk minus xpk minus 1 converges, right? So I mean, what's that? I think all he did was add, I mean, we have the convergence of the sum of differences, right? So what did he do? He just added one thing to that, right? So it's still convergent. I mean, he just added this to it. So the sum of the differences is absolutely convergent, hence convergent. But that's related to the subsequence here. And, well, what happens? I mean, well, anyway, but anyway, yeah. And, all right. So this converges to some element x, which is, you know, in E. And then what does he say? Consequently, I'll trade his consequently for a thus. Norm of xn minus x is less than or equal to the norm of xn minus p, my bad, x sub pn, plus the old add zero trick again, followed by triangle inequality, right? So let us review just a bit here.
So both of those sections converge because the x sub n is, the x sub p sub n is subsequent to x sub n.
Right, so for n sufficiently large, this goes to 0 because it's a Cauchy sequence. So if we take difference of elements in the sequence, this goes to 0 because of Cauchy. We've assumed Cauchy. This goes to 0 by construction of the up here. So the whole thing goes to 0, which is exactly what we want. We just proved that an arbitrary Cauchy sequence converges, which thus shows that the space is complete. Yeah, yeah. The next theorem is much easier. This one next here. I'll write it here. Theorem closed vector subspace. Not really. I mean, you were sounding like so many robot butlers. Let's see here. Closed vector subspace of a Banach space is a Banach space, is itself a Banach space. So what was your question, Audric?
My question to like the sequence doesn't actually have to converge. It just has to be absolutely convergent. But on the norm convergence, like good.
Oh, I can't quite understand you, but we're assuming here that every absolutely convergent series converges in this part of the proof. So we construct let's see here. I mean, we construct an absolutely convergent series, which therefore must converge by the assumption, and then we use that with this triangle inequality trick to get the convergence that we want. I mean, that's the summary of what happened. I'm sorry, Audrey, like, I just can't make out what you're saying. It's dropping in and out. I'll try to call you on the phone once we're done here, if you have time. Let's see here. So the next theorem is the closed vector subspace of a Banach space is itself a Banach space. And I'm just going to read the proof there because it's pretty clear, right? So the proof is pick a Banach space, look at a closed vector subspace. If you pick a Cauchy sequence in there, then it's also a Cauchy if you have a Cauchy sequence in the closed vector subspace, it's still a Cauchy sequence in the total space. So like the Cauchy condition applied to a subspace is still giving you the Cauchy condition for the superspace in which it lives. Therefore, because we're in a Banach space, it converges, right? And then since F is closed, you have, you think about it, right? You've got a sequence of elements in a closed subspace, right? It converges. So remember, if it's a closed subspace, it's equal to its closure. So we're talking about the limit of a sequence. It has to be in the closed subspace. There you go. We just took an arbitrary Cauchy sequence in a topologically closed subspace of a Banach space, and we got that it converges to another point in the space, which is to say that the subspace is also a Banach space. So, right. Ah, yes. So, I think I've got a message here. Oh, nope, that's the previous message. Sorry, Audrey. Okay, this is important. Well, yeah, it's important. So we have seen that not every space is complete, right? There's any number of normed linear spaces which are not complete. The neat thing is, there is a general construction to take any incomplete space, right, and formally extend it to a larger space which is complete. This is called the completion of the space. So let me describe how that's done, all right? That's page 24 here. So we're now talking about the completion. Of a normed linear space. All right. And so the normed linear space we think of as a pair, right? E with a norm. Then the pair, let's see, his notation is E tilde, My advisor would be happy. Dr. Football has put tilde on everything. And then sub 1, because why not? This is called the completion, is the completion. And I say, I really shouldn't say they, yep, he hasn't used the word the, a completion of E, because it's not unique. There might be more than one way to do it. But if it is a completion, it has the following properties, yeah? So, A, there exists phi from E to E tilde, which is 1 to 1. Let's say is injective, yeah? So it's a 1-to-1 map. Such that what? More than that, it's linear. Phi of alpha x plus beta y is equal to alpha phi of x plus beta phi of y. And that's for all x and y in the vector space and alpha and beta in the field. So this is, this could be real, could be complex, okay? I suppose it could be other things too. It could be other fields, all right? And not just that it's an injective, it preserves distance, it preserves norm. The norm of x in the original norm is equal to the norm of the image of x, well, the new norm, right? For all x in E. And C, the image of the original space is dense in E tilde, and D, E tilde, is complete. Now, this is not explaining, this so far, I'm not explaining what the completion is, all right? Excuse me, I am explaining what a completion is. I have not explained how to actually accomplish this, right? How do you actually construct this E tilde? What dark magic do we use, I think this is important because whatever this is, right? If you think about the rational numbers, right? The rational numbers with respect to the absolute value function form a normed linear space because the sum of any two rational numbers is rational. And this, and if we look at rational numbers as a rational vector space, okay? So nothing real here, just like rational numbers as a rational vector space. It's a normed linear space with respect to the absolute value function, right? But it's not complete because, well, pick your favorite example. Mine is the digits in the decimal expansion of the square root of 2, right? 1, 1.4, 1.41, 1.414, dot, 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 right? This is a sequence that converges. Where does it converge to? It converges to the square root of 2, which you have proved a long time ago is not rational. So that proves that the rational numbers are not complete. So whatever this is, if we can do this to the rational numbers, we get a complete space from it, right? And we can actually, that will be the real numbers. The completion of the rational numbers with respect to the absolute value function, the regular one, that's the real numbers. You can make that careful. Okay, so, and here's what he says. He says, a space E tilde satisfying these conditions can be formally defined as the space of equivalence classes of Cauchy sequences of elements of E. So, here we go. What do?